I promised you a simpler way to analyze this situation. We're going to do that. We're going to use energy, and it looks like that camera could go up just a tad. Okay, we're going to use concept of energy. We know that the work done by the net force acting on an object is equal to its change in kinetic energy, and we know that the kinetic energy of the ball when it starts is equal to the kinetic energy of the ball when it ends, because it starts from rest and it ends up at rest. Kinetic energy 0 here, kinetic energy 0 here. Now, what's the net force? Because the work done by the net force is equal to the net force multiplied by the displacement. Okay, it's the dot product of the net force with the displacement. The problem, of course, is we have two net forces. We have a net force on this part of the ramp. We have a net force on this part of the ramp. So how do we calculate the work done by the net force? Well, that's just the work done by the net force on the first ramp plus the work done by the net force on the second. Okay, the net force on the first ramp is just what we'll call F1 parallel, the vector force F1 parallel on ramp 1. And that's just the component of the weight vector in this direction. And I say F1 parallel, and I really don't want to use F1. I should use the weight parallel on ramp 1, the weight parallel on ramp 2. I'll probably change that. But for now, we'll just say that F1 parallel is the force parallel to the ramp on ramp 1. F2 parallel, the force parallel to the ramp on ramp 2. And that parallel component we've seen comes from simply resolving the weight vector into components parallel and perpendicular, well, perpendicular in this case, to the ramp. Now, when we calculate the work, since we have two different forces acting, we calculate the work done by the first force for the first displacement. So that's going to be F1 parallel times your delta x1, where delta x1 is the vector from here to here, and F2 parallel times delta x2. Delta x2 will be the vector from here to here. F2 parallel, the force, net force acting in this direction. Now, F1 parallel is what? It's the weight times the slope S1. And then it's times a unit vector in the direction of the motion down the incline. That vector is just parallel to the delta x1 vector, so that the weight times S1 will be the magnitude of a vector that we multiply by the delta x1 vector that's in the same direction. And if you apply the definition of the dot product, you see that that's just weight times S1 times delta x1. Now, F2 parallel is what? Well, that's the weight times S2 times a unit vector in the direction of F2 parallel. Now, the unit vector in the direction of F2 parallel is down the incline, whereas delta x2 is up the incline, although both along the same direction. So that when we multiply these out, we get a magnitude, weight times S2 times delta x2, but the unit vector, or the direction of this vector being opposite the direction of this vector, makes the dot product negative. So we get 0. Well, obviously we get 0. So we get this equation. Now, you could also reason this out. You know that the work done by the parallel force acting on the weight is positive here. You know it's negative here. You know the distance here is x1 and that it's in the direction of x parallel, f parallel. You know that distance here is delta x2 in the direction directly opposite F2 parallel. So without reverting to unit vectors and dot products, you could reason out this equation fairly easily. I didn't write the unit vectors in because they're in different directions. It would complicate the diagram just referring to them. Whichever way you understand this, best to understand it both ways. It should be clear that we get this equation, and when we solve this equation, what do we get? We get, I'm not going to run through the algebra solving it, but add this to both sides, reverse sides, so you got delta x2 over here, divide by weight times delta s2, the weights will divide out, and you're going to get s1 over s2 times delta x1, which is essentially the same equation. I think maybe I called this x01 or x10 in the previous, but it's the displacement down the first graph. So we get the same result, but we don't have to go through all of the detailed analysis. The whole concept of work and kinetic energy leads us to a much simpler solution than the one we encountered before, where we had to get our hands all dirty with all the symbols and all the equations of motion. We bypassed the equations of motion. So we bypassed the equations of motion to get the result for x2, for delta x2. Of course, having bypassed the equations of motion, we don't have a result for the time, and we might want that, so we might be back with the analysis of the motion. And we did this by using the work energy theorem. That probably called the work kinetic energy theorem, that the work done by the net force is equal to the change in kinetic energy. Okay, the small slope approximation. Well, first of all, if we rearrange this equation with the multiply both sides by the S2, reverse both sides, we get this equation that S1 delta x1 equals S2 delta x2. S1 delta x1 is the vertical drop of the ball. It's very easy to calculate that. We're just multiplying the slope by the distance we travel, and if you do that, you get actually, if you multiply the slope by the distance you travel, you do get the vertical drop, assuming you're going downhill. If you multiply the slope times the distance you move uphill, you're going to get the vertical rise. Again, very easy to prove that. Now, the vertical drop, turns out, is related to the work done by gravity. Okay, and in fact, now this isn't, okay, this is the vertical drop. The work done by gravity during that vertical drop can be depicted by the weight vector here and the delta x1 vector here. These vectors aren't at right angles since we do have a slope, so that if we sketch this and if we do the projection, we see that the dot product is just the product of this projection vector. So this is what we call the weight parallel. Getting a little bunched up there, apologize for that. Parallel component of the weight. And this is delta x1, so that the dot product is the weight vector times the delta x1, which is the parallel component of the weight vector times delta x1. And that equals the weight parallel multiplied by delta x1. Well, the parallel component of the weight is just what I called F1 parallel here. So we could just call that F1 parallel times delta x. Similarly, the vertical rise, we've got our delta x2 and the weight vector. To do the dot product, we have to project back this way, so here's our weight parallel for the second part of the incline. And we see that work by gravity is, again, the weight vector dot the delta x2 vector. Okay, so that's going to be the parallel component of the weight on the second ramp multiplied by your delta x2. And that'll be your F2 parallel times delta x2. Now let's look back over here for a minute. Okay, when the ball is here, then by virtue of its position with respect to gravity, it's capable, in moving from here to here, it's capable of picking up a certain amount of kinetic energy. If there's no friction, then the amount of kinetic energy it picks up is equal to the work done on it by the gravitational force, as we've seen here and as we've seen over here. Then it gets here, and by virtue of its velocity, it's capable of moving up to this position. Now, in moving from here to here, it gains gravitational potential energy, losing its kinetic energy in the process. So, as we move from here to here, we lose gravitational potential energy. Gravity does work on the object, and this thing we call gravitational potential energy decreases. As we move from here to here, this thing we call gravitational potential energy increases. Now let's look back over here and get something close to a definition of what we mean by gravitational potential energy. The work done by gravity here is F1 parallel times delta x1. That's what we think of, that's how we define the lost gravitational potential energy. We lose gravitational potential energy from here to here. Gravitational potential energy goes down, kinetic energy goes up. Okay? And then from here to here, we gain gravitational potential energy, and here's the work done by gravity when we gain the potential energy. You can see that when we lose gravitational potential energy, gravity does positive work. When we gain gravitational potential energy, gravity does negative work. So this is kind of a first picture of potential energy, and we'll go on to talk more about potential energy in the next video clip.